Adjunct Faculty at LUMS and a Faculty Associate for the Center for Water Informatics and Technology. She's also a visiting researcher at the International Water Management Institute and has worked extensively not only with the World Bank in DC, but also for the Center, also at the Center for Watershed Sciences in Davis and with the Harvard Water Security Initiative. Laila is going to be discussing groundwater science and then following up with Hydrology.
Thank you. I was quite nervous that all of you will get very bored with technical information. I was sharing these chairs with Adil. How technical should it be? So if I get too technical, stop me and tell me to explain something. We will do enough technical so that you understand why we model our own systems the way we do. Adil will actually be more hands-on with the modeling and always be cognizant that models are not reality, just a representation. And so our own understanding of physical processes shape the model that we develop. Yeah? Echo, let me reduce. Is this better? No? Is this better? Okay. So just an overview, we're just going to look at the basic terms and basic groundwater hydrology that you should know. Then movement in flow, what is the main equation that shapes flow, some of the groundwater challenges from a scientific perspective, and some of the management options. Groundwater, as the name suggests, is water found in the pore spaces under the ground. It represents 0.6% of the hydrosphere. If you were to gather all the water in the lakes and the rivers, all of the surface water, groundwater is still 35 times more. You must have seen this flow chart. If you look at the entire water on the Earth's surface, 97% we can't use, only 3% is fresh water that's usable. But of that fresh water, majority of the storage comes in ice caps and the rest in groundwater. So the amount of water that we can get from the ground is much, much more than we can get from surface water. In essence, what it also says is groundwater is two things.
Groundwater is two things. I think I'll just speak loudly. So groundwater is a form of storage. So just as reservoirs store surface water, groundwater is an excellent form of storage, but it also prevents evaporation. And when a lot of us who are surface water engineers, we think we need to improve efficiency, so we line canals. When you do line canals, be reminded that you won't necessarily save water by lining canals. The water that is in the canals gets infiltrated, so it feeds into the groundwater aquifer. In essence, people use that groundwater aquifer through tube wells, they extract it and use it for irrigation purposes. So, canal lining will not necessarily lead to water efficiency, and always remember that a lot of people make an argument that we should line canals, make reservoirs. While that's not a bad thing, remember that it may not actually achieve the objective that you want. Try it. No, not sure. Yeah, exactly.
Is this better?
Yeah.
So actually there's a very good paper, I can put the link on the wiki site, which talks about how we try to save surface water but at the cost of groundwater. So some terms that you should know when you're dealing with groundwater, if you want to pursue something later in learning about how to model it, there are two terms, porosity and permeability, that determine groundwater flow and groundwater movement. Porosity is the percentage of space in the rock or surface that is filled with water. So soil has a lot of space between it, it's very porous, right? A pumice rock has a lot of spaces. Porosity determines the ability to store water, not necessarily the ability to transmit water. Permeability, on the other hand, is the capacity to transmit that water. So if you have a lot of spaces between between the rock particles, you are porous. If those spaces are not connected, you are not permeable, you are porous. Often sediment that is shaped differently is less porous because the big particles, there are spaces created between them are filled by the smaller particles, right? So this is low porosity because the shape, it's a mixed sediment, right? You have big particles and the smaller spaces are filled. This is highly porous. There's a lot of space because it's less mixed. There are fewer particles in between. And permeability is when they're not even connected. So these boundaries, if they're not connected spaces. These both terms will determine how much water can flow through the soil surface. So the amount of saturation means the amount of water in the rock spaces determines the different water zones, right? So at the top layer you have the unsaturated zone. This is just below the ground. There's a lot of space. There's a lot of openings and voids. If they are not, usually in the unsaturated zone, those voids are not completely filled by water. That's called the unsaturated zone. Here, there is not so much water, not so much pressure from that water either, right? So then below that you have the capillary fringe. Here, what is going to be moving up through capillary action and suction force. Below that you have the water table and the saturated zone. So the saturated zone is the zone where all of the spaces between the rock particles are filled with water, not with air. So imagine if you have a tank of sand, right? If you pour water through it, the water will settle at the bottom due to gravity, correct? And then as you move up, the quantity of water at the sample, it won't be as dense. It will collect at the bottom. That's exactly what happens under the ground. The lower space is known as the saturated zone. All of the spaces are filled with water. The top of that layer is known as the water table, or the phreatic surface, you can also call it. Below, between this and the unsaturated zone, water is moving up through capillary action. Saturated zones also, so here is a better description. This is your saturated zone. The vadose zone is also the unsaturated zone, right? And it's moving up through capillary action. So water comes, you can look at the moisture profile. The water content is highest here below, and upwards it's getting drier. If you were to define the water table is the surface that divides the unsaturated zone and the saturated zone. If you were to determine the water level, if you want to see how much water level, what's the water level under this ground, you will dig a well, and the water at the surface will give the water level. So sometimes you can find a perched water table. This is even in the unsaturated zone. So saturated zone, the top of the saturated zone is the water table. Then it's the unsaturated zone. In the unsaturated zone, you may find a perched water table which is completely separated like this. So this is supposed to be your main water table. You find a water table number 2 because some kind of impermeable material will be here. Impermeable means that you can't flow through it. Usually what happens is that water, if there's rainfall, it infiltrates and goes down. This is a permeable layer that it allows water to pass through, right? In this layer, water can't pass through, so you get perched water tables. An aquifer is the saturated zone. It is not contrary to what you may have as an idea. A lot of you may think there's a layer of entire water in the ground. That is not correct. It's not an entire layer. It's called an aquifer. It's still rock particles. It's a body of saturated rock, but there's a lot of rock with a lot of water. All of the porous spaces are filled with water. And you get two kinds of aquifers. You get the unconfined ones and the confined ones. So the unconfined aquifer, here I want to show you this. The unconfined aquifer is basically your saturated zone. It's open to the surface. And the water table here follows the level of the ground. The confined aquifer follows if there's a confining layer. The confining layer is called an aquitard or an aquiflume. The confining layer separates the confined aquifer from the unconfined one. So going back, so in the unconfined ones, it can get recharged very quickly because it's open to the surface. It's higher up. So when there's rainfall, it infiltrates and it enters the unconfined aquifer. The confined aquifer can only get recharged by lakes and rivers. It can't get recharged by rainfall because the water can't permeate through. An aquitard is any layer of rock that prevents water to go through. There are a few kinds of aquitards. So this is again description of an unconfined one. This one, so it's open to the surface. You can get recharged. If you build a well here, right? If the level of the well is here, what happens is the water level surface will be the same as the surface in this unconfined water table. In a confined water aquifer, it's under high pressure. The water is under very high pressure, so if you dig a well, the water pops up and goes upwards. And this surface is only recharged by lakes, right? So nothing can flow through this layer. This is your aquitard. Water can flow through and infiltrate here, and it can come through here. This is that lake. So a lot of people, aquitard, aquiflume, and aquifluge, they're similar. They're all layers that confine. An aquitard is a general term that you use. It's a formation with low permeability. Again, the definition of permeability is the ability to transmit water. So aquiflues and aquifluges are forms of aquitads. Aquiflues, they do contain some water, but they don't transmit it, right? So they may be porous but not permeable. Aquifluges don't contain or transmit, so they're completely hard rock. And then confining beds are also used to describe rock units that have low permeability. I'm not going to define the term hydraulic conductivity yet. So all these three restrict movement, and aquifluges don't even contain water at all. So if we have the entire, if we were to draw a cross section of the Earth's surface, the open surface, the water would go through the radar zone into an unconfined aquifer. And then is the zone of saturation that you get the confined aquifer. Semi-confined aquifer is something in between. These are also known as liquid aquifers. Often aquifers don't fall neatly into two categories. Sometimes the permeability in some areas is very low, so they can become confined because the upper layer becomes confining. In other cases, there is permeability, so water can flow through. So those terms, the term aquifer, aquitard, porosity, permeability, you should have an understanding of. When you are supposed to do a model, you must have a conceptual understanding of whether the aquifer that you are going to model is confined or unconfined. So moving on to groundwater movement. When you have rainfall, some water can flow over the surface. That is your overland flow. It flows very quickly and drains the rivers. Unfortunately, with groundwater, it takes years to millennia for water to flow, and that can be problematic, right? If there is any level of pollution, that pollution will be concentrated in that area. Have you heard of this in our intro water treatment class? And we said the solution to pollution is dilution. Must have read it, right? So basically, whenever you're drinking water, there's some limits that you set in varying forms of concentration. So I can have a level of lead, a level of mercury before I get poisoned. With groundwater, if you get mercury, it's not going to be diluted. If you throw some mercury in the ocean, it will get eventually diluted and the movement is faster. Groundwater, the movement is extremely slow. The velocity of groundwater is determined on permeability. Again, this permeability means the ability of the soil particle to be able to transmit water, not store but transmit. The slope of the water table. So if the water table is extremely, it's at a very high slope, then the water can flow quickly, and that's due to gravity. And it's inversely proportional to porosity. If you have too much porosity, then the water just stays there and gets stored rather than moving. So porosity is good for storage, but it's really bad for movement. So permeability and porosity are both dependent on the kind of material you have. You can have sand, sandstone, rocks, granite, and together you can clump all of these characteristics into a term called hydraulic conductivity. Hydrogeologists and hydrologists use the term K for it. K means hydraulic conductivity. When you do a model, there are some parameters you need. You need to know the water level, you need to know a lot of things, but one of the major things that you need to know to determine groundwater flow is K. K is determined through experimentation and calibration, and it's completely dependent on the kind of media you have. Hopefully, this will not be as complicated. I will try to make it as simple as possible. So, if you all remember in grade 5, you must have learned speed is equals to distance over time. And then if you got advanced, you learned that speed can be called velocity, right? So everybody knows speed equals distance over time. So, if there is a pipe, right? Actually, let's just refer to this one. It's easier. You have this pipe, right? This pipe, imagine if this pipe is of length L. So, what you're going to be measuring in terms of velocity is there, so it's going to be, hold on, I'll derive it, it's probably going to be easier. So, we have velocity is equal to distance over time. What we use instead of time is the change in length. So we use this as the length. So how this works is, what we're going to measure with velocity is the change in the height difference, and this is through fluid mechanics. The change in the difference in the water level gives that slope over the change in the length. Is your Darcy velocity. This was determined through an experimentation, which translates again into distance over time. But they calculated time to the length and use the head difference as the change in distance. Because it's not water, it's water flowing through the sand, there is some factor in the porous media that stops the water from flowing, like some frictional force. That force that we use is called K. K again is your hydraulic conductivity. It depends on porosity permeability. When you are going to be doing any kind of flow through subsurface soil or through soil, you will not do directly velocity distance over time. You will be doing dot-C flow. For simpler purposes, often you use any layer of soil will have different hydraulic conductivity. What you end up doing is there are two types of hydraulic conductivity. There's going to be a vertical one and a horizontal one, right? Vertical conductivity would be how quickly the water can flow from in a vertical fashion to the soil. And then the horizontal one is how it can flow horizontally. There won't be a gravity component to it. So you clump it by using the term transmissivity. And the reason for that is you have a layer of soil, but that soil is actually a number of soils of length B, right? This is B1, B2, B3. And then this one has K1, K2, K3 as a hydraulic conductivity. To get the entire total hydraulic conductivity of this, we use transmissivity, which is multiplied, your K is multiplied by B. So it's going to be K1 times B1 plus K2 times B2 plus K3 times B3 to get the overall hydraulic conductivity. The term we use in it is transmissivity because it takes into account the thickness of the soil component that contains that particular hydraulic conductivity. So any layer of soil that's thinner but has high hydraulic conductivity will still have low transmissivity. So one of the ways that we can induce groundwater to flow slightly, move faster is through digging wells. Wells are basically holes that are dug into the ground to reach the aquifer. You can make wells in the unconfined ones and in the confined aquifers. In the unconfined aquifers, this is the aquifers open to the surface. The water level is not at such high pressure, so it follows the same path of the water table. In the confined aquifers, it may reach to a level above the confined aquifer because the water is at very high pressure. You must have heard of hot springs. Hot springs are like wells in confined aquifers. You dig the water and the water gushes out because it's at very high pressure. If you pump, you basically force groundwater from other sources to come towards that pump because you create a pressure difference. This also causes water from all of the other layers to go down. So you can use wells to move groundwater faster. If you pump a well, what happens is there's a pressure difference, the water flows upwards, but then the water leaves from this area and you form this cone of depression. Over here there is no water. So how water moves upwards is it moves radially, it takes water closer to the well and then spreads wider. So these cone of depressions can lead to, if they are not recharged, they can lead to permanent lowering of the groundwater table. In Pakistan, the situation is even more complex because we just don't have wells. We have tubewells, we have hand pumps, we have terrace systems, and we have springs. So we have multiple sources of groundwater that we can take water out of. And to understand how they all are connected, nobody has really done an extensive study looking at that. We know that if there are two wells, their cone of interference can touch one another, and if they do, the water table can drop drastically. With craze in the place and tube wells, this is definitely a more complicated system. So it brings us to a few of the challenges. And the first one is overdraft. Overdraft means taking out more water than you are recharging. Groundwater is replenished and recharged by infiltration. So if you have rainfall, if you have some form of water coming into the surface, your unconfined aquifers at least can get recharged. Your confined aquifers will get recharged by lakes and rivers. For confined aquifers, it may take years for them to recharge. Water moves very slowly. It's not like reservoir. You have water and you store it there. A lot of people think that even artificial recharge is very easy. It takes a lot of time for water to move. You can't make a hole and throw in water and expect the aquifer to be recharged that way. If you do withdraw, and withdrawal is faster than recharge, the water table will drop. And at a certain point, there may be permanent flowing. That is when the aquifer will collapse. When you sucked in so much water that there are no spaces left and there's compaction. So, if you had a surface, if you had a hydrological unit like this and you reduce so much, you form a cone of depression. Overdraft eventually leads to subsidence. As I told you, you have permanent flowing, but then if you use too much of the water, then the ground subsides. The ground subsidence means going down, right? So the water surface, the ground surface lowers down because the water is holding the ground in place. The water fills up all these pores. Imagine if you have a sponge. It has air, it has water. If you squish it out, if you squish the water out, its volume will decrease. And that's what can happen and can lead to huge depressions or karst topography that's unequal terrain. This has happened extensively in Quetta. There has been a study done by the University of Balochistan that they found that there's been huge subsidence, and the cause for that has been groundwater. The groundwater table has also lowered over the past few years. You also hear it in places like California and Louisiana, but at home turf it's quite a common problem and we haven't given it enough attention. The third issue that you can have is contamination. And in fact, contamination is probably the biggest problem with respect to groundwater. There was a recent study done by DFID and it was done by the British Geological Survey. Alan McDonald, it was just released a few months ago. And what they found was that yes, there has been lowering of the water table, but what is alarming is the quality of the groundwater. It's our native groundwater is very alluvial, but what they found were heavy metals. The movement of these metals is very slow, and we rely on groundwater even for drinking. So there's no way that we are cleaning up this groundwater, and it can present a lot of health effects on it. It's problematic because when groundwater does become contaminated, it's not as easy to clean up. It's not one, as I said, it's not like one, it's not that you dig and there's a nice convenient pool of water like that. It's spread out throughout the ground surface. It interacts with the cations and anions in the ground. Right? There are ways of cleaning up that groundwater, but even something as simple as any organic matter if it goes inside, it can cause groundwater to attract more heavy metals. So anything that we throw into the ground will eventually affect all of the interactions of the different minerals in the ground. And it's not easy to clean up. Surface water, you can treat it, you can find it in one convenient pool. You cannot find that in groundwater. It's also colder, so reactions take longer. Why does that matter? Because if you have organic matter, you want that organic matter to decompose. You throw a lot of things in the ground, you think they're biodegradable. When they're inside the ground, they take much longer to decay. And on a human time scale, it may not happen within our lifetimes. I had a video, I was trying to find a video about arsenic contamination, but the video quality was not good. This video is about something that happened in Niagara Falls, a story of Love Canal. So the History Channel made a documentary about this piece of land that was bought by a school, and they found out that chemical company had dumped in all the waste, and it basically devastated their groundwater, and they made a huge evacuation zone. It's very interesting. We'll watch some of it because it's really epic. Sound is not there.
Turned out to be one of America's most notorious toxic waste forest stories. An inadequate cover on a chemical company's dump site allowed a deadly brew of toxins to leak into a suburban neighborhood. A public health scare erupted. Over 900 families left their homes. Several years and hundreds of millions of dollars had to be spent to try to stop the further spread of the contaminants. The Love Canal originally got its name from entrepreneur William T. Love. In 1894, he began construction on a man-made canal that he envisioned would link the Niagara River to Lake Ontario.
His plan was to use the power of the river as it rushes towards the falls, diverting it before it goes over the falls, and carrying it north through a canal which would wind up at this escarpment or cliff and pour down and provide the power that's necessary to generate electricity.
The canal was essentially a trench dug in the clay soil of the area. After only 3,000 feet were excavated, a pair of unforeseen events brought construction to a halt.
One was the depression of the 1890s, severe depression. Secondly was something Tesla devised a way to have alternating current instead of direct current, so you didn't have to be right on top of the source of power.
Alternating current made it unnecessary to develop industry adjacent to its canal.
What ended up happening, it's an interesting story. It was very important for, between the 80s and 90s when this happened, it shaped the entire narrative about why water is important. It was one of the Rachel Carson and stories like this. They heralded an environmental movement around human health. When we think about water and we think about water management, we think about irrigation, power, food, we don't think about health. And there's a strong linkage. What eventually happened is there's this chemical company, they had dumped in all of their pollutants in a lake a long while away from the Niagara cities and then covered it up. And that all of the chemicals leached into the groundwater, and there was a piece of property that was sold for $1 to an entire school. And the children basically started getting very unwell, and some actually died. So all of the mothers became very concerned and decided they're going to sue the school.
And then the school didn't know anything about this. So then the school teachers and the parents, they found out, and this took actually around 15 years, and they're still cleaning it up. So today, this area is, you know, like a museum. The story is that people did not live there. The effects you can still see. Just as fear of nuclear disaster is created, groundwater contamination can create a lot of problems. In Bangladesh, the arsenic issue is pretty, severe, and heavy metals and any contaminant that enters your body through groundwater can be very severe because its concentration is high. As a human being, you can be exposed to a particular concentration of chemicals, but given that the chemical concentration is so high, that exposure is beyond your limit. In Lahore, the situation is also not any better, and I think there should be a stronger recognition of that. We have a long, large network of unlined sewage drains. Water leaks from all of these drains to all of the shallow aquifers. There are deep ones and there are shallow ones. In the Mazang area particularly, have you all been to Mazang, Mega High Court? The irrigation department is not in a very clean area that way. There's already a cone of depression there. It's an unconfined aquifer, it's saline and it's shallow. So even though it gets regularly recharged, there's a lot of drainage that happens from sewage. The contamination issue is something which is a greater challenge than the quantity issue. Water quality is a bigger problem with groundwater than water quantity. That's one thing that you all should take away from this. The fourth issue that we see in coastal areas is saltwater intrusion. What happens basically is there's a density difference. In coastal areas, because there's a density difference between regular fresh water and saline water, what happens is that salt water starts entering the groundwater interface. There is the interface is a boundary between the salt water and the seawater, the salt water and the fresh water. And that interface is not exactly clear, but there is regardless an interface. Then you start pumping, for example, this is the interface. If you start pumping, for example, here, what happens is this salt water will start intruding in. This is your ocean. It makes this section salty. And this is your fresh water, and this is an interface. There is a general principle. If you were to measure how far this level is, what you do is you measure the ground level, and you measure the you can basically see that there's a relationship based on density difference that has been developed. If you take two pots of water, one filled with salt water and one filled with fresh water, the elevations will be different. Gravitational potential energy rho GA. So what happens is that fresh water, the principle is that fresh water is 40 times less than it's 40 times more. So the interface is going to be the distance between the ground to the saltwater seawater interface is 40 times more than the water table. And this principle is called the Ivan-Herzberg relation. And it's derived basically on purely density differences. So, if you do have a pump well, what you end up seeing is that this interface changes. Because the water table will change. If your water table goes down, so will your distance to that interface, right? if the water table is 1, then the distance to the interface is 40. If your groundwater table goes to 0.5, then your distance to the interface will be 20. And we use it as a tentative measure. So if you go to a coastal area and you ask someone, excuse me, can you tell me how high the water table is? And if they have a sense to tell you, then multiply that by 40, that's when you start finding saline water. When you do have pumping and that interface changes, that is known as upcalling. So you've gone through 4 of these challenges and there are ways that you can manage it. There was a term that was developed, safe yield. It's been defined differently. Initially it was just defined as the amount of water that you can take in from a well, which is equal to or less than the recharge. Which means that the groundwater, whatever your annual recharge is, extraction should not exceed it. But now they've even said that it should not in any cost lower the water table, and it should fall into your existing water rights. So you should be protecting not only your amount of recharge, you should also be making sure of rights. This term, the safe yield term, has been criticized, so it was instead replaced by sustainable yield. Sustainable yield means how much you're going to take out, right? So sustainable yield is the long-term amount that you can withdraw to meet your uses without compromising on long-term sustainability of that aquifer. So you now have to move away from that well area to the aquifer area. The idea is that groundwater is also an intergenerational issue. Safe yield is only short term, sustainable yield must be long term. It must be that I withdraw enough water that I can meet my uses, but not enough that I affect my future generations. So this concept is being introduced and more people are writing literature and doing models to determine sustainable yield as opposed to safe yield. If you were to look at an aquifer sustainability, so you have the supply of that aquifer which comes through recharge, and then you have the demand side usage, right? So if you have a shallow aquifer, residence time means how much time that water will stay in that particular space in groundwater, right? So residence time is important for pollution purposes as well as movement purposes. If it stays there too long, it's not moving fast enough. So in a deep aquifer, recharge rate is very low, 0.5 centimeter a year, very low. In a shallow aquifer, it's still greater than 10 centimeter a year. And in a deep aquifer, the residence time is also very long, so the water will stay there. If it gets polluted, it will stay there. There's no way of mixing, it's not changing. So if you affect a deep aquifer, you can cause real damage because there are very few ways that you can fix it. If you were taking out, say, 1 centimeter a year, this is assuming that you take 10 liters per person a day and you have 3 people per kilometer square, you're basically taking out 1 centimeter a year. And say you take 60 centimeter for irrigation. What you will find is that maybe your shallow aquifers can sustain these uses, your deep aquifers cannot, because they are not getting recharged sufficiently. The extraction is 60 centimeters a year, but the recharge is only 0.5 centimeters. So when you think about aquifer sustainability, you look at all the ways that that aquifer is getting recharged and you measure that. And then you think of all the ways that it is being extracted and you measure it. And then you see how it lines up. And in a time scale of millennia, if you are not able to make sure that that groundwater remains there, then that is unsustainable. So one way of groundwater management is you basically control pumping. You reduce the pumping rates and the number of pump wells, and that's also a very difficult thing to do because some people may argue that groundwater pumping is better than surface water, because surface water goes to waste when it goes into the ocean, you don't use it, and with groundwater you get it according to your own time, and so you can use less. Then you can artificially recharge it through ponds, so you make more ponds and water bodies that will recharge your confined aquifers, or you can use imported water. You can basically also use a number of pumps to pump in water through the barriers into the confined aquifer, and also do fresh water injection. Now, these are all artificial methods, and perhaps Saval will touch upon it. What can economics basically do to fix this problem of groundwater management? We use groundwater mostly for irrigation, and irrigation is an expensive user. So is there a way that we can move our water from lower marginal value uses to higher marginal value uses? Basically, it means that where can we use less water but get the most from it, and in which sector? It can also touch upon virtual water. Maybe the answer is outside of the water sector. That maybe we're using too much water. There's a huge debate on this going on in California, because they're in a drought and they've invested so much money in this water system. And the debate is that why have we invested so much in a resource that's in short supply? We should have enough to supply water for drinking, but for irrigation and agriculture, is it really giving us so much benefit? As water becomes more and more scarce, the cost of supplying that water to irrigation and agriculture is also going to get much higher. And can irrigation and agriculture actually provide a sufficient justification for it? So maybe the solution is outside of even the water sector. So regardless of whatever management technique we use, it's important to keep in mind what our objective is, and I think I'll bring it back to the hydrological table. A lot of people will line canals, as I said, in the efforts to reduce water wastage. It's not water wasted when water seeps into the ground. Right? When water is returned back, a lot of farmers feel in the Varabandi system, when you get surface water, they want to use all of it because they think it will go to waste. But actually it won't. It will just seep into the ground and it will feed into your groundwater aquifers. So, and the other thing is that these groundwater systems in themselves are pretty complex. We may want to manipulate them, but we may not. They've done a bunch of studies. If you introduce more organic material to the groundwater, it changes the concentration of heavy metal to phosphorus and nitrogen ratio. All of the different cations and anions, their concentrations change if you introduce any foreign chemical inside groundwater. And we may try to be making improvement in water. Any change that we do can actually negatively affect it as well. Again, I want to speak about efficiency and infiltration, because there have been billions of dollars of investment in our irrigation system to line it and to reduce inefficiencies. And perhaps it's worth looking at whether there are inefficiencies or unauthorized uses, right? Like if there are unauthorized uses, then you need to talk about groundwater governance rather than water efficiency, because water that infiltrates only feeds back into our aquifers that we do use. And if our groundwater aquifers get depleted, then we will rely more on surface water. The water that we're not getting from the surface, we will get from the ground, or vice versa. So it's not that you will actually create change in using less water. Surface water and groundwater must go hand in hand. And then the issue of scale in groundwater is important, because whatever local wells we have, at a larger scale, they can affect overall extraction and water tables at a regional scale as well. Different management options can be tested with models. Right? Groundwater systems are difficult to understand, and a model is the best representation of them. They're also a better representation to understand whether an aquifer is confined or unconfined. What we did in the beginning, basic terms, they're not very easy to monitor or measure. It's not easy to know porosity, it's not easy to measure permeability, it's not easy to know whether this aquifer is deep or shallow, how far or wide it goes, whether it has boundaries. Nobody knows, nobody's really done a very comprehensive study of how this aquifer looks like. What you do is you make a model, you test it with real observations, and you see how tested and observed compare, and then you recalibrate that entire conceptual model as well. So, you have physical models, there are ways of doing modeling. Physical models are expensive. For groundwater, it's very difficult actually to do them, but you do use physical models for determining hydraulic conductivity. If you want to see how permeable the soil surface and sand surfaces, you will actually use a physical model. But in terms of a larger scale, pumping effects, we're going to use mathematical models that our colleague Adil is working with the PMI in the irrigation department. They've done quite a bit of groundwater modeling. And so the idea is what kind of questions you can solve from a model. You can see what are going to be the expected groundwater levels in the Lahore in 2020, as well as how will a change in stream stage at River Ravi affect the water table. So if we have high water levels in the rivers, how is that going to change the water table in the aquifer? Capture area for a field, well, you want to see to what extent a well can actually tap in water resources, how large its influence is, right? To what extent will the zone of depression be created if we dig a well? And what is the likely pathway of contaminants? So, groundwater modeling is groundwater flow modeling and groundwater transport modeling. And transport basically looks at how do you move metals in groundwater, metals, chemicals, so contaminant transport. These two things go hand in hand, and models are the best way to model these. Even things such as how many wells can we dig in the coastal area, and how will that affect our seawater, freshwater interface. So for all of these answers, we do seek models. And to the best extent, without doing these models, we won't get insights as to our own hydrogeological units underneath the ground. It's very difficult to figure out the shape of the ground underneath, and you have to use certain models for it. So I hope that this presentation has at least at a scientific level presented some of the challenges, and these, if you work in the groundwater unit at the irrigation department, kudos to you, because it's very difficult to, it's out of sight, but it's not out of mind, right? Groundwater, you can't see it, but it does have devastating impacts. And the idea of I wanted to show that video is that it looked like a very peaceful community. There was a river flowing, but the groundwater was entirely contaminated and people started getting sick. So groundwater comes, it's not just about the irrigation and agriculture. A bigger issue is our own health. And more recent studies have particularly focused that there's been arsenic in the ground, and the reliability of groundwater, although it is there, in terms of water quality, it may not be. And given its residence times and given low recharge rates, that it's better to prevent any damage from happening than taking remedial action later on. I've taken questions, or we can begin with the next one. Question?
That was very fascinating. Actually, there's a lot of groundwater model in terms of economics and uses very simple hydrology and development, and that the hydrologists and what the scientists have done. But there's one kind of key thing that we use in linking an economic model with like hydrological model is the specific yield parameter, and that kind of has to do with like the storage of the water in the aquifer. And I wonder if that is to some extent related to the porosity parameter.
So specific yield, the formula for it basically it's a measure of porosity, and specific yield means how much amount of water can be extracted from a unit of rock, right? So specific yield in a way is the yield. I don't know how you guys model it in, it's basically a measure of storageivity. You know how we did transmissivity? So storageivity and specific yield in that way are related. They measure the storageability and they are factors of porosity. So porosity is the term that we use in groundwater more model is storageability or storage coefficient, and it's related to specific yield. I think one is unitless and the other is with units. The storage coefficient is basically the specific yield before pumping and the specific yield after pumping. So they basically use that to measure storage. So they are in that regard linked. I think the greater challenge is not even figuring out these parameters, but making a conceptual model of the aquifer. It's very, it's nice that we see everything fall in neat layers, but it's not actually in neat layers. The problem is that for each layer, there are different hydraulic conductivities at every x and y axis, right? So if hydraulic conductivities are a function of x and y, so that creates a lot of parameters. So what you often do for a model is that you get an average hydraulic conductivity for x and for y.
So I'm not a technical person, but I should my water. It's interesting in sort of understanding whether groundwater science and hydrology allows for the mentioned story, you mentioned how when the cavities in the water how there's pressure that affects the recharge. I was wondering if there is a way for us to model how overdraft in one area
Can affect it in the other.
and is affecting overdraft yes, in terms of the whole aquifer, and also from the smaller units in terms of, for instance, at a district level, how overdraft, or at within a district level, at the town level, at the residential zone, how overdraft in the DHA affects the rest of the world, or how overdraft in the hall affects surrounding areas, or how overdraft in the shoe affects in the industrial area affects the surrounding areas.
Yeah. The challenge with that is at a local scale it's actually much more doable because there's a formula that you can use, a Dupuit, it's called Dupuit equation. Depending on whether it's a radial well, the kind of well, whether it's confined or unconfined aquifer, you can. The issue is that we don't have enough data of how many sources of extraction there are. For example, like if you have the Carré system, you know that there's going to be a cone of depression. You can easily find out how deep and how wide that cone is by finding out, if you know the recharge rate, the rate at which you are extracting water, like how much volume per unit time you're taking out. If you have that, if you have the width of the circumference and width of the area, you can easily measure it. The problem is that 5 meters down you find another well, and then 10 meters down you find another. Their interaction is usually modeled through model flow, right? There's a very open, easy access, open source model model flow. You just put in where you have the wells, and you can model it. Then you can use in piezometric wells to measure how the water level changes. The thing is, the first model, you can easily calibrate it and all. What that model will tell you is that your initial understanding of how the conceptual model is different. If you find out something as, oh, the hydraulic conductivity was not right, or this was not an unconfined one, it was actually a confined aquifer, or it was not confined, it was unconfined. And it gives you insights and then you make it better. Like, but you can get all of these insights. Yeah. If you want to model, it's very easy. You need just a recharge rate and the number of wells. If you can get that information, all of the other information, you can build up, right? You can look at a soil map and try to figure all of the other factors out. But if the key issue is even having a network of knowing where the wells are, nobody knows that. Nobody, we can't even keep track of surface water and have huge losses in the system and can't figure out where that water goes. So when it comes to groundwater, a lot is extracted and a lot of people do not report it. I mean, in Texas even they haven't figured out how to monitor groundwater.
Thank you. I agree with that gentleman that presentation is fantastic. But I just want to add something where you mentioned that on the basis of outcomes or the benefits, we must divert irrigation water to some other center. But in my opinion, that the benefit from the irrigation is not the money per acre or the dollars, but it is also include the calories per acre, oxygen produced per acre, or the labor consumed per acre. So, keeping in view that perspective, we are not simply divert the water from the irrigation sector to any other sector in terms of.
Absolutely. It's always, I think Sarah's presentation is deeply with it. When you have a scarce resource, you want to make the best use. But my argument there is more based on what are our priorities. To me, and I hope to everyone, the priority should be that every human being in Pakistan should have access to water for drinking, and then they can move on to irrigation. I think irrigation trumps all water uses in terms of power, and that's how our irrigation network works. The problem sometimes is that people don't have clean drinking water. So I think that's an issue of poverty as well, which we can address. But there's no, every country decides on what its national priorities are, and what the resource people will, that's your objective, so we will optimize the model according to that objective. If the objective is something else.
Yeah, I'd like to comment on your statement that the losses from the canal is huge after there. Like in Punjab, 50% of the aquifer is saline. So seepage into the saline zone is mostly. So you recover only about 50% of it. And when you line up the canals with the water courses, we are talking about half of the benefit of it. You achieve hydraulic efficiency in the fields, which reduces usually amount of water that you use.
That's
But rather a complex thing. And even for the recharge of the saline zone, you might argue it leaves the sewage flow. So it doesn't matter if you have a recharge in the saline zone also. But I think it's not such a.
There's
you can't give a very simple statement.
I absolutely agree. There's someone who said water management is provisional. If you solve one problem, you'll basically come up with another one. When they try to make tube wells, they want to stop waterlogging and salinity. With tube wells, there's an issue of now water table lowering and overdraft. If we fix that, we are bound to get another problem. And I think that comes with the territory. If you're doing something right, then you solve one problem, just naturally move to the other.
more wasteful uses only in that region as compared to other parts?
My understanding is it's more populated, so Mazak area was first developed. It was the area that was initially known as Lahore. I've not actually done sufficient modeling to comment on that. I think the irrigation department, the Irrigation Research Institute, Mr. Mohammed Javeed and a few others probably have worked on that groundwater body. But from just common sense, I would guess that it's more populated. There are also, like, all of the sewage canals are unlined, so the water seeps into the ground. And more is being extracted in terms of drinking. For most other areas, they're more developed, so they have the pipe networks there. They don't have to dig wells or get water from the ground. There was a newspaper heading a few months ago, earlier this year, they found that most places in Lahore, you can't drink the water from the ground. So I don't think that it's really drinkable, but often it's the only choice that we have. And with a lot of chemicals, there's a particular level that our human bodies can reach. But the accumulation builds up. If our own bodies can biodegrade it over time, then it's fine. But if it doesn't, then it accumulates. Like mercury, for example, is very poisonous. With organic matter, I believe it's very high. We still use it quite a bit. But it hasn't affected our health in a horrible way, but it does affect our health. It's pretty bad. Yeah, last question. Part of it, yeah. Often that even when you're doing your water balance, they basically account the surface water irrigation networks, and they use that as an indicator for all kinds of water uses. So they're not mutually exclusive. In fact, all of the other uses of water are secondary to irrigation water. You make a pump for the nutrients, that quantity of water is very, very small compared to how much you're going to use for the trees. It's almost negligible. So it's not mutually exclusive, and it usually falls into that same category. Most of the people who done water balances and based on water balances, they use industrial water and irrigation water as the only extractions, because the amount of water, industrial would also, you take it to a cleaning plant and then you get bottled water. But the reality is the amount of water that you're taking for maintaining it is very small.